Hi, Algebra 2. This is your third day of radicals, and we are actually going to be focusing on radicals and exponents. You have learned exponent rules several times, but we're going to really be focusing on that today. A little side note, and I'll write this up here, and put a little star by it. There is something called rationalizing the denominator, which you all, as Algebra 2 students prepping for higher math, should realize what rationalizing the denominator means. However, you will not be expected to do this on your SOL test, so this is an extra topic right now. For example, if I have a number divided by a radical, so let's say I have radical 3 in the denominator, it is inappropriate in the math world to leave a radical in the denominator. It's kind of like an incomplete sentence. You're not supposed to leave it like that. So when you see the words rationalize the denominator, what it means is let's do something to get rid of that denominator, to get rid of the radical in the denominator. And what we can do is, if you think about when you multiply by the same radical, radical 3 multiplied by radical 3, I'm going to wind up getting radical 9. Radical 9, because it's 3 times 3, is now a perfect square, so my denominator would wind up just being 3. So that does, in fact, get rid of my radical in the denominator, because now I just have 3. However, I can't just multiply the denominator by the radical 3. It would throw off my fraction. But I can multiply by 1. If I multiply any number by 1, it doesn't change the value, right? So square root of 3 divided by square root of 3 is the same as 1. So that means I'm really just multiplying by 1 here, and I'm not really changing 2 divided by radical 3, my original problem. I'm not changing the value of it at all, I'm just changing the way it looks. So if I multiply by square root of 3 over square root of 3, I will not have a radical anymore in the denominator, which is what I wanted. No radical in the denominator. And I will have one left in the numerator, but that is okay. It is right in the math world to leave a radical in the numerator, but not in the denominator. All right? So no radical in denominator. That is what I'm going for. In my numerator, I'm going to have 2 multiplied by root 3. So I will have 2 root 3. And again, just keep it as 2 root 3. But my whole goal was to get rid of the radical in the denominator. All right? And this is when I have a monomial denominator. That just means when I have one term in the denominator. So what would it look like if I wanted to rationalize the denominator? Let me grab my red again. And I have a binomial denominator. So in other words, what if I had 2 divided by 3 minus, and let's do root 5 this time. I still have the same problem. I have a radical in the denominator, and I do not want that radical in the denominator. Well, I'm also going to multiply by my radical 5, but because it is a binomial, if you guys think back to how we factored a difference of squares, we wanted the same first term, the same last term, and in the middle, when we had a difference of squares, we had 1 minus and we have 1 plus. The reason why this might work with this is because when you have a difference of squares, when you FOIL this, your inside combination, your inside product, and your outside product winds up canceling out. And then I'm really just dealing with the 3 times the 3 and the square root of 5 times the square root of 5, which will also cancel out. So let's see what happens here. Let's say I just multiply by the opposite, right? And we will use the word conjugate. The conjugate is really what your opposite of your denominator is, because it's not really opposite, but it's the same first and last term, just with an opposite symbol in the middle, so between them. Instead of a subtraction symbol, we're going to use an addition symbol. If I wind up doing this, my denominator has to FOIL, right? Because I have 2 terms, a binomial, multiplied by another binomial. So 3 times 3 makes 9. Then I have 3 times root 5, so I get 3 root 5. And then my negative root 5 times 3 is negative 3 root 5. That's what I wanted to happen, because remember, those will cancel out. And then negative root 5 times positive root 5 winds up being negative root 25. Again, that's a perfect square because it came from 5 times 5. So when I simplify this again, all right, there we go. 3 root 5 minus 3 root 5 is 0. Root 25 is 5, so I just get 9 minus 5, which is 4, right? And my entire goal of doing that was to get rid of the radical in the denominator, which I did. The radical is no more in the denominator. So again, I can't just multiply the denominator by 3 plus root 5, so I have to also do the same thing to the numerator. And this will just distribute, so 2 times 3 is 6, plus 2 times root 5 is 2 root 5. All right? Oops, there we go. So I just want to show you guys that because you might continue with math in the future, and you will have to know what it means to rationalize a denominator, because a lot of times it is inappropriate to leave the radical in the denominator. IB tests, so if you take any IB classes, actually they do not care about leaving a radical in the denominator. However, AP and future and higher math will see it as inappropriate. All right. So now that you know how to multiply radicals, you can now rationalize the denominator. Let's talk for a minute about rules of exponents. And we are going to go through these each one by one, and we're going to practice them all a lot when I see you guys next time. So rules of exponents you have now seen in Algebra 1. I think you even saw them in 8th grade math, in 6th grade math. But you definitely practice them a lot in Algebra 1. And we're going to revisit them in Algebra 2. Rule number 1 is anytime that you have a number raised to the 0 power, it is equal to 1. For example, if you have 5 raised to the 0 power, it is 1. All right? If you have, let's say, 3x divided by 5y, but it's raised to the 0 power, that means it simplifies down to 1. No matter what it is, if it's raised to the 0 power, you get 1. That's rule number 1. Rule number 2. If you have a number, oops, I covered it up with my 2. Let's try that again. If you have any number, there we go, that is raised to a negative exponent, the negative in the exponent tells you that that the base, this a, actually belongs in the opposite location than where it is currently. So see how this a right now is in the numerator. However, it has a negative exponent. That means that my a actually belongs in the denominator. So for example, if I had 4 raised to the negative 3rd power, what that actually means, my 4 right now is in the numerator. So it actually means the reciprocal. My 4 really belongs in the denominator. And since it's in the denominator, which is what this negative tells me, it's raised to the 3rd power. Well, when nothing is in the numerator, I can always have a 1 in the numerator. So when that negative exponent is telling me the reciprocal, 4 raised to the negative 3rd power means that 4 to the 3rd actually belongs in the denominator, and I just have a 1 in the numerator, just like I would have had a 1 if I put a denominator for the original problem. Or let's say I started off with 1 over 2 to the negative 3rd. This negative means reciprocal. So since my 2 is in the denominator, the negative exponent is telling me to move it to the numerator, and then once you move it, you can change the exponent to positive, just like here. Once you move it, the exponent is positive because that negative is telling you to move. It's telling you to take the reciprocal. So as soon as I take that reciprocal, it's now, the negative is gone. All right? Now this will look a little bit more familiar. Rule number 3, anytime that you have a base that's the same base with different exponents, my bases are multiplying, my exponents add. For example, if you guys you've done this a million times, you probably didn't even realize that this was one of the exponent rules. But if you have x squared multiplied by x to the 5th, right? You wind up with the same base. You still get x's, but you have 2 x's here, you have 5 x's here. They're all multiplying, so I have a total of 7 x's. because my x's are multiplying, but my exponent, the 2 and the 5, means that I had 2 x's here and 5 x's here, so they add together and make 7. It's very important, though, to realize that your bases are multiplying, your exponents, these numbers, right, the 2 and the 5, those add together, okay? Bases multiply, exponents add together. Now, what if I had a coefficient, like 2x to the third multiplied by 4x to the, fourth. There we go. I am multiplying my bases. So the 2 multiplies by the 4 because those are both coefficients. They're whole numbers. 2 times 4, that makes 8. I'm also multiplying x cubed times x to the fourth. So I still get x's, but I have 3 x's here, 4 x's here, so I have a total of 7 x's. So my coefficients still multiply, my exponents add. Let's look at rule number 4, again, a pretty familiar one. If you have a base with a power divided by the same base with the different power, your exponents wind up subtracting. So for example, if I started off with x to the 6th, and then I divide by x to the 2nd, I have 6 x's in the numerator, 2 x's in the denominator. So that means 2 of my x's can cancel out, and I wind up with only 4 x's left. Okay? So I had 6 in the numerator, 2 in the denominator. 6 minus 2 gives me 4. Well, what if my numerator had less? What if I had x to the 3rd divided by x to the 10th, right? I have more x's on the denominator. I don't have as many x's in the numerator. So I can still subtract. I'll get 3 minus 10, I'll get negative 7. Well, let's look back up to rule number 2. When I have a negative exponent, that means that it's the reciprocal. So that actually is my x belongs in the denominator. Once I move it, I can change my exponent to positive 7, okay? So remember, this is a combination here of a couple rules coming together. Let's look at number 5. When I have a base raised to a power, and then it has parentheses, and that whole term right here is raised to a second power. What happens is I'm saying I have this inside term this many times, right? The n is telling me how many times I'm multiplying a to the m by itself. So what happens is these wind up multiplying by each other, m times n. For example, if I have, let's see, x to the 4th, but then I raise it to the 3rd. What I'm saying is I'm going to take x to the 4th 3 times. So that means I'm really going to have 12, right? X to the 12th. I'm going to have 12 x's by the time I'm done. Be careful with this one because let's say I have a coefficient like 3, x to the, 2nd, and then I raise it to the 3rd. I'm not only paying attention to the x because this big 3 is also inside the parentheses. So that means this 3 must also raise to the 3rd power. So 3 has to raise to the 3rd power. And x squared has to raise to the 3rd power. 2 times 3 makes 6. So I really have to make sure that both of the terms inside the parentheses wind up getting that exponent. Well, 3 to the 3rd is 27. All right, and then I'll get x to the 6th. All right, we are almost done. If you have rule number 6, if I have 2, which is what I just did actually, this example over here, if I have 2 different a coefficient and a variable or 2 different variables inside parentheses and then I raise it to a power, I just have to make sure that it applies to everything in the inside. So for example, this is actually exactly what I did right over here. If I have, let's say, a 2 and an a squared and an x inside parentheses, and then I raise it all to the 4th power. Okay? What I'm going to have to remember is that the 2 raises to the 4th power, and the a raises to the 8th, and the x raises to the 4th. I went ahead and filled in the next three rules as we went over radicals the other day, and we will practice these when